we talked about this competition experiment where we were determining which nucleophile would be the best, right? And we determined that which nucleophile here was the best nucleophile, the hydroxide or the acetate? It was the hydroxide. And why was the hydroxide, given that it's an O minus and acetate is an O minus, why is hydroxide a better nucleophile? Okay, and why? That's right. So acetate, we have resonance structures which delocalize that negative charge over two oxygen atoms, whereas hydroxide, that single oxygen atom is negatively charged, right? And so if we were to run this experiment, we would actually find that the secondary alcohol, cyclohexanol, would be our major product, and that our minor product would be an ester. And so we could determine those molecules through a variety of techniques, some of which Dr. Pigza was talking about that she uses in her laboratory. So in terms of being able to determine whether or not a reaction is going to go through an SN1 or an SN2 reaction, you need to know something about the nucleophiles and electrophiles, okay? And you really need to commit this to memory. And again, I don't say that often in organic chemistry because it's almost always a relative argument. But there are some things that you need to commit to memory. And that is that nucleophilicity usually parallels basicity, but not always. Okay? This idea of steric hindrance can actually lead to less nucleophilicity. Okay? So if we think about the example here where we have ethoxide and tert butoxide, ethoxide is actually the better nucleophile. They're both oxygen minus. There's no resonance structures to either one of them. But ethoxide is the better nucleophile because it has less steric hindrance. What do I mean by that term? Less stuff in the way. That's exactly right. And so ethoxide is both a Lewis base and a nucleophile. Tert butoxide is a base, but it is not a nucleophile under most conditions. So remember the rule I told you that all nucleophiles were Lewis bases, but not all Lewis bases were nucleophiles, right? There's the first example you're coming to. Tert butoxide, whether it be potassium tert butoxide, sodium tert butoxide, or lithium tert butoxide. We don't care about the counterion at this point, okay? Tert butoxide is going to function as a base, but it rarely, if ever, functions as a nucleophile. Okay, so with that in mind, what does that mean that tert butoxide is going to like to react with? Nucleophiles attack carbons, but what do bases attack? Protons, that's right. So if we want to react in our molecule at some proton, let's say to do an elimination, which we'll learn more about in the next chapter, tert butoxide would be your choice because it's not going to function as a nucleophile. So if I want to do an SN2 reaction and somebody says I need to use tert butoxide as a nucleophile, we know that that's not going to work, right? We got to find some other way to make our reaction work. So steric hindrance is very important. So the more branching, if you will, that we have close to the nucleophilic atom, the worse the nucleophile it's going to be. Okay? So here we've got one carbon and two hydrogens on the carbon directly attached to the O minus. Here we've got three carbons. This is big and bulky. And so why would this not favor, what is it about steric hindrance that keeps it from acting as a nucleophile? Aubrey, you kind of alluded to it. You said there's a lot of stuff in the way, but what do you mean by that?
The negative can't get in there to bond as well.
Okay, that's right. So remember, in an SN2 reaction anyway, right? The nucleophile has to approach from the back side, and that nucleophile actually has to come into contact with that carbon's antibonding orbital, right? And it's got all this stuff around that's kind of protecting it, right? So you can't get in there and do the chemistry, so to speak, right? So primary alkoxides work really well. Tertiary alkoxides, not good nucleophiles. What about a secondary alkoxide like isopropoxide? Something like that. Yeah, it can function as a nucleophile, but is it going to be Is it the reaction going to go faster with this or with ethoxide? Faster with ethoxide, that's right. Okay. Now, solvent also has an effect. And one of the things that most chemists are guilty of, 99% of the time, is we just treat solvent as an inert substance that does nothing. And that is absolutely 100% incorrect all the time, okay? And so imagine that we have a nucleophile. Let's suppose we're using bromide as a nucleophile. And so we place it into water, right, because it'll dissolve in water. We don't have Br minus just floating around in solution, right? What we have are solvated ions. So the cation is solvated by water through this dipole ion interaction or this lone pair cation interaction, however you want to think about it, okay? But you've got an ion, and of course the water's a polar molecule. Water will associate around the cation. But the cation's not what is responsible for the reaction, right? For the most part. Now, if we think about bromide, what's around it? The hydrogens from water, right? Think of it as you've got your nucleophile with a coat on it, with some clothes, okay? It's covering it up. It's blocking it. Is that going to help the reaction or hinder the reaction? It's going to hinder the reaction. That's right. And so basically they think of this as hydrogen bonding, but really it's two dipole ion interactions. And you've got this coat of water around it. So the solvent, water, is going to speed up an SN2 reaction or slow down an SN2 reaction? It's going to slow it down. So what can I do? Pardon? Run it dry. What do you mean by that? No water in the reaction. Okay, so maybe I can pick a different solvent that doesn't do this, right? Okay, good. So when we have what are known as polar protic solvents, we're talking about water and alcohols, anything with a heteroatom hydrogen bond. We call those polar protic solvents. So it can be water and alcohol. It can be some amides. We'll learn more about some of those later. It turns out that the nucleophilicity increases as you go down the periodic table. As I go from fluoride to iodide, the nucleophilicity increases in polar protic solvents. Okay? That goes counter to basicity, right? And I was talking with my daughter yesterday who had a question about organic. She's also doing the same thing you guys are doing right now in organic chemistry, all right? And she was wondering, why is it that fluoride is a worse nucleophile than iodide, even though fluoride, right, is more basic than iodide? And you remember that little rule we talked about at first that has to do, it parallels basicity? Well, that's true in a period, not in a family. Yeah, it's true in a period, but not in a family. And the reason that it's not in a family, because as we go down the family, what happens? The size gets bigger, the atom gets more polarizable, right? The electron cloud is more diffuse, but also it doesn't hydrogen bond as well with the solvent. Okay? So the big iodide actually has less solvent around it than the tiny little fluoride. Okay? And so it's got less quote-unquote clothes around it to get rid of before a reaction can occur. Okay? So as we go down a family in terms of nucleophiles, nucleophilicity increases. So what's more reactive, an oxygen nucleophile or a sulfur nucleophile? Sulfur. How about a nitrogen or a phosphorus? Very good. Okay? Now there are solvents that we can use in organic chemistry that are not protic, and we call these polar aprotic solvents. Okay? They are polar. They will dissolve a number of things like water will, or fairly close to how water will, but they have no oxygen-hydrogen or nitrogen-hydrogen bonds, okay? And you need to know these. Acetone is a good example. Acetonitrile is a good example. Tetrahydrofuran, which we abbreviate as THF, is a good example. DMSO is kind of the classic example, dimethyl sulfoxide. It will dissolve a lot of stuff. In fact, just for your information, DMSO is used in medicinal chemistry to help transport drugs across the skin and other membranes. it'll transport things. It helps dissolve them and transport things across the skin, etc. And so it actually has some issues in the laboratory because you could get something in there and transport it across your skin that you don't want to. So you got to be careful when you're working with something like DMSO. Dimethylformamide is another polar aprotic solvent. And then HMPA is a highly, well, it used to be used quite a bit, but it's not used quite so much anymore because it is highly carcinogenic. And so we don't have undergraduates working with HMPA. But it is a solvent that is polar and is aprotic. Does everybody agree that all these solvents are polar and aprotic? You see that?
They don't have a proton.
If you look at all the heteroatoms, there are no hydrogens on any of the heteroatoms, right? That's why it is polar aprotic. Well, polar because you've got a dipole, obviously, but no NH or OH bonds. Okay, so these can't hydrogen bond. So if my nucleophile is a halogen, how much solvent is going to be around it? It can't form hydrogen bonds, so very little. We call these solvents polar aprotic solvents because they can't hydrogen bond with the nucleophile, and they make the nucleophile, for lack of a better term, again, this was all created by men many, many years ago, naked. These are naked nucleophiles. They are not clothed. They are ready to react, okay? And so if Grace was to come into my laboratory and run an SN2 reaction in alcohol and run the same SN2 reaction in acetone, which reaction would be faster? Acetone, because the acetone is not going to solvate the nucleophile as strongly, right? And so the reaction should proceed quicker, okay? And so that's what you're seeing here. If you look at the counterion, we still have ion-dipole interactions, right? Because we have the dipole from acetone. It can form those ion-dipole interactions with the sodium cation. But we no longer have hydrogen bonding to the nucleophile part, or the anion, right? We do have solvent around it, but it's not really bound. It's more of like a dipole ion interaction that's really weak, okay? So yes, there's some solvent there, but notice we're not drawing any bonds to anything. And we know that breaking bonds takes energy, right? And so that's going to slow the reaction down. Here we really don't have strong bonds involved in the solvation, and so the reaction doesn't have to expend a lot of energy to do that. And so we say that these anions are naked. They don't have a solvent shell surrounding them or clothing them, if you will, okay? Now, in polar aprotic solvents, the nucleophilicity increases in the opposite direction. Now it does follow the basicity rule, right? So as we go from iodide to fluoride, the nucleophilicity increases in polar aprotic solvents, okay? Think about it. If you're going to do an SN2 reaction, the atom has to come in from the back and attack. So a smaller negatively charged atom should be able to do that easier than a larger negatively charged atom, right? And that's true, as long as there's no solvent around it. But when we're in polar protic solvents, fluoride holds onto that solvent really, really tightly. Okay? That's how it exists. That's what stabilizes it. And it doesn't get rid of that solvent very well. Whereas iodide can fluff off that solvent, no problem. And the reaction will go quicker then. So the take-home message here is nucleophilicity depends on the atom, it depends on steric hindrance, and it depends on the solvent. Okay? A lot of things are coming into play here. So let's try to predict the likely mechanism of a substitution reaction. Let's suppose that Matthew has this alkyl halide, cis-1-bromo-4-methyl-cyclohexane, and he takes 2 flasks and he puts an equal amount of this in one flask, he puts an equal amount in the other flask. In flask, let's call this flask A, he adds water and sodium hydroxide. And in this flask, he just adds water. He puts the reactions, say, on a hot plate, heats them up, and lets them stir for a given period of time. what's going to happen in each reaction? What are the products going to be? The top will be an alcohol, and the bottom will be an alcohol as well.
Yeah, I did this problem on Saturday when I put alcohols above and I got it wrong.
It's both alcohols. They are both alcohols. But there's stereochemistry to take into account, right? If we take the reaction to be SN2, what will the stereochemistry of the product be? Pardon? It'd be trans. That's right. The OH would be trans to the methyl group, right? And why is that? That's right, because we go through inversion of stereochemistry, correct? So if I have a cis molecule and the nucleophile comes in and kicks out the leaving group, now it's going to be trans, right? What if it goes through an SN1 reaction? Will it still be cis? There will be some, and then there will be some that are trans. We'll end up with a mixture. And why is that? What's the intermediate that we go through in an SN1 reaction? We go through a carbocation intermediate, right? So the bromide leaves, we get a carbocation, and now the nucleophile can either come in from the top or the bottom. Does it have to be 50-50? No, but it's not going to be complete inversion.
Majority cis, wouldn't it? Majority trans, because that road line will still be there, kind of injured.
Your reasoning is fine with that, yeah. I mean, in terms of the ratio, but we're going to get a mixture, right? So if we have a strong nucleophile and a good electrophile, in this case it's a secondary alkyl bromide. Bromide is a very good leaving group. Secondary can do both SN1 and SN2, but we got a strong nucleophile. That's going to favor SN2, and this is the only thing you'll have in your reaction mixture. SN2 is more favorable when you have strong nucleophiles and primary, secondary, or methyl alkyl halides. Here, we have the same electrophile, but now we have what kind of nucleophile do we have? We have a weak. So it can't come in and do an SN2 reaction. It has to wait for the leaving group to leave. So the leaving group leaves. We end up with a secondary carbocation, which is okay. And now the water can either come in from the top or it can come in from the bottom. We get these carbon-oxygen bonds that we need. Obviously, we have 3 bonds to oxygen, so it's positively charged. The bromide comes in and abstracts, and you get HBr as an acid that comes off. But if it comes in from above, we have the cis isomer, and if it comes in from below, we have the trans isomer. Okay? So we could determine the ratio of products based on what kind of techniques have you learned? How could we determine whether we have the cis isomer or the trans isomer? Can we use polarimetry here? Is this a chiral molecule? It is not a chiral molecule. It is optically inactive. But I think you all will agree that this molecule, the cis isomer and the trans isomer, are related to each other how? Are they enantiomers or are they diastereomers? They're diastereomers. That's right. They are not the same compound at all, right? And so they will have different physical properties. So what else could we do that you all have learned in lab that would be able to detect the two? You could do melting point. What else could we do? Could do TLC, right? If we run the top reaction and we did TLC, we would see the disappearance of our starting material and the formation of only one product, correct? If we ran the bottom reaction and watched it by TLC, we would see the disappearance of our starting material, but we would see the appearance of 2 new products, the cis and the trans. And so that could be used as evidence that the reaction is going as mentioned, okay? So there are some things that you need to know to predict the likelihood of an SN1 or an SN2 reaction, okay? And so leaving group is very, very important. So the better the leaving group, what? The faster the reaction or the slower the reaction? The faster the reaction, that means that the transition state's going to be lower. Is that going to favor SN1 or SN2 or both? Both. That's right. So better leaving groups always favor both. So an SN1 reaction will go faster if it's got a better leaving group, and an SN2 reaction will go faster if it's got a better leaving group. So just based on that, we can't make a decision per se, right? We know that solvent plays a role. Polar protic solvents favor the SN1 reaction. Polar aprotic solvents favor the SN2 reaction. Okay? So if Sayer comes in and sets up a reaction, it's going to be a substitution reaction. She throws it into water. Most likely it's going to be a SN1. Aubry comes in, wants to do essentially the same reaction, but he uses acetone. Chances are the mechanism is going to be SN2. So being able to identify polar aprotic and polar protic solvents is very good. I will stick to the examples that I've given you here. So it's a good idea if you have trouble memorizing them, that's a good thing to put on your note card, okay, for the test next week. Okay? We also need to know the types of, we've already learned a lot of chemistry. SN2 and SN1 gives us a lot of stuff. Right now, from alkyl halides, you can make alcohols. You can make ethers, just like Dr. Pigza was talking about just a few minutes ago. We can make esters. We can make nitriles. We can make alkynes. We can make azides. We can make amines. We can make thiols. We can make sulfides. We just need an alkyl halide with a good leaving group and to pick one of these nucleophiles to do it. Right? It is that easy. But you will make it so much more difficult on yourself, I promise you. And when you get more experience, I promise you, it'll come a lot more naturally, okay? It takes time. Now, in organic synthesis, quite frequently, we are given a product that we want to make. This is medicinal chemistry, for example. You go to work for Pfizer, they have a compound that they've identified that's a medicine. They hired you as a chemist to make it. We know what we want to make. We have to figure out the best way to make it. So here is the product that we want. How do we make it? We make it through a process called retrosynthetic analysis. Using the reactions that we know and the product that we want, we work backwards. It is thinking backwards. It is not backwards thinking. Okay? And it's very, very important for all of you who want to go to medical school. Why? Why is this skill so important for you when you get to medical school?
Well, if you want to be a doctor, you have to usually find, someone usually comes in and they're sick, and then you have to work backwards.
Exactly. Exactly. Your patients come in, they've got a fever, they've got a cough, they've got a runny nose, whatever the case may be, and you have got to work your way backwards to what the likely cause is. And there's a lot of things that have a high fever, a cough, and runny nose. And in that process, some doctors will say they are not scientists. I argue with them on this. Because you're doing the scientific method. You're making an observation. You are working back to what you think the likely cause is, which is going to be your hypothesis. Doctors don't call it a hypothesis. They call it a diagnosis. And then you're going to test that hypothesis. And how do you test that hypothesis as a physician? You treat it, right? And so Sarah comes in, she's got a fever, I think she's got an infection of whatever kind, so I give her an antibiotic and I tell her to come back and see me in 2 days. If the fever's gone and she's feeling better, chances are my hypothesis was correct and the treatment proved that. If she comes back in 2 days and says, Dr. Masterson, I feel worse than I did 2 days ago, my hypothesis is wrong, I have to reevaluate, I have to do something else. This way of thinking will drive you crazy in this class, I know, but it will be a very valuable skill that you learn. And everybody that I've ever sent off to medical school has told me that. No, I'm not trying to figure out how to make alcohols on my patient, but how to make alcohols and work my way back has taught me how I need to think from an observation back to a likely cause in medicine. So, given the reactions that we know, how can we make that alcohol? We need an alkyl halide. So I've got this alcohol that is going to be my product, and I'm going to think backwards. And this arrow, like this, is called a retrosynthetic arrow. It means I'm going one step back. So what do I need? You said I need an alkyl halide. Where does the halogen have to be? Pardon? She's not sure what I said, so that's okay. It's this bond we need to make, right? So if I start off with this alkyl halide plus what? What? Why would I use hydroxide and not water? It is stronger. It is a stronger nucleophile. And why else would I choose it over water? Is stereochemistry going to be an issue here? Do I have a stereo center? No. You're not wrong, but it's not relevant here, right? So what kind of alkyl halide is that? Is it? It's primary. So do I need to do SN2 chemistry or SN1 chemistry? I need to do SN2. And why do I need to do SN2? Pardon? It does, but why? If it was SN1, this would have to leave, right? And what kind of carbocation would I get? Primary, secondary, or tertiary? Is that good? That's not good, right? So I've got to do SN2 chemistry. So SN2 chemistry is favored by primary alkyl halides and strong nucleophiles. That's what we picked, right? And so that's what we just did. Okay, so we will pick up with eliminations after the exam, which is on Wednesday, right, in this class? We have the exam on Wednesday?
Do we have a after school review?
We will arrange something, yep.
Monday's going to be a review.
We will have a review. Get together.